You have fallen into Event Horizon with John Michael Godier. Dr. Kipping is the Assistant Professor of Astronomy at Columbia University, where he researches extrasolar planets and moons. Dr. Kipping also leads the Cool Worlds Lab at Columbia, which includes a YouTube channel and a website where you can learn about their research. Dr. Kipping's other areas of research interests also include study and characterization of transiting exoplanets, exoplanet atmospheres, Bayesian inference, population statistics, and understanding stellar hosts. He is also the principal investigator of the Hunt for the Exomoons with Kepler HEK project.
Dr. David Kipping, welcome back to the program.
It's my pleasure to be back on. I feel like I must be getting close to a record of most appearances on the JMG podcast here, right? And I've been on a few times.
Very possible, but that's what that is a product of being prolific.
It's not, thank you.
New paper, and this one particularly caught my attention. The idea of applying Bayesian statistics to how we think about alien life. Not so much looking for it, but how we think about it. And in classical terms, we've always thought about things like the Drake equation and, Kardashev civilizations and all this. But we might have to adjust that thinking. What is your view now, after having written this paper? What is your view now about the framework and how we think about aliens, which was the whole point of the original Drake equation?
Yeah, I mean, the Drake equation has been a useful tool for a long time, but it's also a tool that has been enormously misunderstood and misinterpreted, abused even. And it does have a reputation that has been sullied a little bit because of the number of misuses, I would say. I don't think there's anything fundamentally wrong with what Drake wrote down, especially in the context of the time and the intent of what he was doing, which is really just to organize a meeting. That was pretty much it. But you have now decades of people plugging in numbers and coming up with all sorts of strange answers. So that is already a headache as to whether there's something better than the Drake equation. And certainly many people have tried to reinvent the wheel in that aspect before. The angle I was coming at with this paper was essentially an itch, I would say, an intellectual itch, that for me the Drake equation just really doesn't address at all. And that's that I really would expect that the universe, or any environment, to be honest, be it a cluster of galaxies, a selection of rocks in a pool, whatever it is, that you would either expect that life would be prolific and it would end up on essentially all of the locations where conditions were suitable, or it would be extremely unusual. And the usual case is totally consistent with our existence, because if it only happens 1 in a trillion times of all the planets in the universe, then the fact we are here is totally self-consistent with that. There's nothing that's a contradiction there. Despite our intuition and knee-jerk reaction against that, there's nothing inconsistent with that. So my intuition was sort of along these lines. And intuition's one thing, but that's not rigorous. You want to have some kind of mathematical underpinnings as to justify your argument. And so I discovered this old argument that had come from some of the founders of Bayesian statistics, in particular Edwin James and a chemist called William Haldane. And they had come up with this idea, thinking about a chemical reaction, and in particular dissolving some random chemical into a beaker of water. And they imagined that you had this. I talk about this in my video. We did a little demonstration on the Cool Worlds with my son, Jackson. He helped me out with this. But we had a series of beakers of water on a bench, and we put some unknown chemical into each of these beakers. And it's the same chemical, but the beakers are a bit different. Some of them have a little bit more water. Some of the water might be a little bit warmer or cooler at the parts of the bench. And the question is, how often, a priori, before you've seen any data, that means, would you expect that chemical to dissolve? And Jaynes, the Bayesian hero that kind of kicked things off for over 100 years ago, he argued that you would really expect it to happen either essentially all of the time, close to 100%, or very, very rarely. But it would be very contrived if it was 50-50. If 50% of those beakers of water ended up dissolving the chemical X and 50% did not. And his argument was, because if that was true, then it would mean that, there is some, let's say, some threshold condition for this chemical to dissolve in the beaker. And it would imply that the conditions in the room were just pretty much perfectly set to that threshold point. And so the very slight difference in temperature from one side of the room to the other was just enough to tip the balance. And it'd be very odd if the temperature in the room just happened to be finely tuned to the exact switch point between those 2 points. And he was imagining, in this case, kind of a fairly homogeneous set of beakers of water, but they could be extremely heterogeneous. They could be beakers where some are acidic, some are boiling, some are freezing. They could be very, very different to each other. And the argument still holds. It would still be very curious if the switch point happened to be at exactly half of your beakers. That'd be very odd, because you chose those initial sets of conditions. If you chose the acidity and you chose the pH, the temperature of all of these things, it'd be very odd if that choice happened to line up with the exact threshold point, which you didn't know before you got started with the experiment. So this argument always made sense to me. And I thought, hey, we could extend this to worlds. Rather than just applying this to beakers, let's switch out those beakers for exoplanets, maybe habitable planets, for instance, or it could even be star systems, or even cubic parsecs, cubic light years in the universe, some volume of space. And again, you would kind of expect that given more or less, similar conditions, but even a diverse range of conditions, this should still be true, that either intelligent life, in particular I was thinking about in this paper, would be very, very common, or intelligent life would be very, very rare. And then you come into a problem, because the universe does not seem to be filled with intelligent life. When we look around us, we don't see every single star with advanced alien technology around it, at least as far as we can tell. And it's even inconsistent with Earth's history, because most of Earth's history we know did not have intelligent civilizations on it, as far as we can tell in the archaeological record. So it does seem like there's an issue. If you're in a universe where it's either very rare or very common, the very common situation seems to run into tension with our observations.
I think we can say that much at this point because of, the Great Silence, because we just don't see obvious, unambiguous evidence of alien civilizations. We're not seeing giant beacons and constant flows of radio signals, very obvious technosignatures. We're not seeing any of that. It's all ambiguous hints that are probably natural things that we don't quite yet understand, that nothing is screaming aliens. And as a result, it does seem that the universe is presenting that intelligent life is rare. But this does not speak to life itself. Now, in the sense of life arising and microbes appearing in the universe, this doesn't really hold for that, right?
You could apply James's argument to life, to simple life, whatever it is. You could even apply it to the conditions for life as well. So you could apply this equally to the rare earth hypothesis, or really just, let's not say rare earth, but the earth analogs hypothesis. So you could say the fraction of Earths, true Earth analogs out there, is either a very large number or a very, very small fraction of all the possibilities. You could apply it to microbial life with the same extent. And you could say of those Earth analogs, either microbial life is extremely common or it's very, very rare. And then again, amongst those, that subset, you could then sort of play the game of, okay, intelligent life as well. So you could apply it to any of them. The reason, what's different about intelligent life is that we actually do have, I think, a constraint. And some listeners might disagree with this, but I think we do have a constraint that the fraction of stars which have advanced technological civilizations around them is not close to 100%. Now that's maybe, some people might think that's a very strong claim, and some people might think, well, of course, that's obvious. And it sort of depends on how conspiracy theorist you go. But I would claim, based off all the observations we have of the universe, everything appears totally consistent with a natural universe around us. We don't see giant engineered stars around us. We don't see starships coming out of warp drive, giving these huge flashes of light everywhere we look. We don't see a solar system, when we landed on Mars, a planet teeming with robots or advanced life forms already walking around the surface. So everywhere we go, it seems like the universe is consistent with pretty much an empty place. And then you the problem you run into is, then if you're an optimist and you say, okay, I'm going to run a program to look for aliens, so SETI, the Search for Extraterrestrial Intelligence. I'm going to run a program to look for advanced intelligent life in the universe. you have a conundrum, because we can kind of rule out the situation that Jaynes would argue for, that F is close to 1, as I would say, the fraction F of volumes of space or planets with intelligent life on them. That fraction can't be 1, or can't be even close to 1. So we have to rule that out. On the same side of the coin, or the other side of the coin, we don't really hope that the answer is close to 0, because otherwise there's no one to talk to. It's pretty much a lonely universe. So you're really hoping then that you're in the valley of improbability space that Jaynes said from the outset, this 50-50 situation. It doesn't even have to be 50-50. You can think in orders of magnitude as well. But there's this very deep valley in between where essentially it's extremely improbable. And this really kind of comes down to, fine-tuning arguments. If you measure two completely unrelated phenomena to each other, let's say the mass of the electron and the strength of the gravitational field of a planet or something, there's absolutely no reason why those two numbers should be the same, right? In general, they're going to be completely different orders of magnitude to each other. And yet what we're really asking for here in the SETI context is that we have this kind of fine-tuning balance point where the fraction of planets that go on to form intelligent life certainly can't be 100%, but it seems to be finely balanced where the numbers add up. So we just end up with just enough that there's like this galactic federation out there, but not so many that we're completely alone in the universe, and not so many that it's completely full. And so that kind of poses a fine-tuning problem. And so I kind of asked this question sort of a little bit playfully in the title of our paper: do SETI optimists have a fine-tuning problem? And it does seem from our perspective that there is an issue here. And when we're looking for these advanced intelligent life forms, we might be pushing our hopes a little bit. But when it comes, as you say, for simple life, we can apply the same argument, but we have no constraint on the existence of simple life. It could very well be that the entire universe is teeming with very simple life. That's totally consistent with everything we see outside of our own, when we look through our telescopes. There's no constraint that we have to rule that out. So I'm quite happy with that as a allowed possibility. Equally, I'm okay with the possibility that there's very little microbial life out there. Both of those are basically equally possible, I would argue at this point. But when it comes to intelligent life, it just can't be everywhere, because that goes against our observations, and therefore it nudges you towards this bowl-like mentality of either one or the other. It pushes you towards the reign of pessimism.
What's interesting about this, though, when talking about the microbial side, is that that's something we have a good chance of answering in two ways here on Earth. One is explore the solar system, start, examining plumes from Europa and Enceladus and things like that, and, Mars, Venus, whatever, looking to see if there are microbes there that are distinct from Earth. In other words, they can't be panspermic. They're, a true second abiogenesis in the solar system. Going with that, we also have the people trying to figure out abiogenesis here. So they're going to take a look and try to unravel how, the chemical process that led to biology happened. Both of those offer us a way to determine, and this could happen within our lifetimes, it offers us a way to determine if microbial life is probably common or probably rare. And if it turns out that it's very common and we find it at, 3 or 4 different places in the solar system, then we can look out there and say, yeah, there's microbes out there. But Earth's history tells us, though, that you need a lot more than a microbe to reach a technological civilization. And as you said, Earth only did it once. And it just seems that's a huge stumbling block, that perhaps it just takes so long for a planet to achieve intelligent life that we might be just a fluke, a really early fluke. But what does this say, extending these statistics forward, about the future of the universe? In other words, does this change as time goes on? In other words, does the likelihood of a civilization appearing at the same time as another one nearby increase with the age of the universe?
I think you could easily apply sort of monkeys on a typewriter type logic there and just say, well, obviously the longer the time span, the more opportunities there are to have two contemporaneous civilizations with one another. So in that sense, it's definitely possible. But at any one given snapshot of time, I think it would be equally unlikely that you would have two civilizations within shooting distance of each other. So I don't think it fundamentally changes the communication aspect. Of course, the communication aspect was what Drake was focused on. And I think a lot of us have almost given up on that idea. And when SETI first started, it was actually CETI, not SETI. It was communication with extraterrestrial intelligence. And it was quickly rebranded to search because I think a lot of us realized that the idea of actually having a two-way conversation when we can't even communicate with, in other intelligent species on this planet is a little bit fanciful. So how are we ever going to have these meaningful conversations with other aliens? Let's just maybe simplify the problem, just try to detect their existence or not. And certainly Drake was thinking about that. Drake's equation, I just want to come back to it for a moment because it's not obvious what maybe is different in our approach, but I think we were able in this paper to sort of really circle back and understand a deep connection that really proves that our formalism of thinking about this, a dichotomy, you would say, between two extremes, can be linked very naturally, actually, to what Drake was writing about. And the way we approach the problem, we say that Drake's equation basically has one big problem with it, and that's that it's unbounded. So you can actually plug in numbers into the Drake equation. If you have no information about any of those numbers that go into the Drake equation, you can plug in anything you want. In fact, you can plug in numbers so large that you can have more intelligent communicative civilizations than there are worlds in the entire galaxy or stars in the entire galaxy. So you can easily, run into a problem where there are more civilizations than stars. That's obviously a problem, and that shouldn't happen. And the reason why it shouldn't happen is because in any ecological system, be it a petri dish or a forest or a garden or a galaxy, you can't really have more civilizations, more life forms than there is substrate. In the video I talk about sort of mold on a piece of bread. The mold can only spread to the extent of the bread, and once it's eaten up all the bread, that's it. And so when you look at the population of microbes in any kind of system, they kind of exponentially explode in terms of the population. And then they kind of rapidly grow, and eventually they taper off until they fill basically the entire galaxy. And so you get this kind of natural filling behavior. So imagine this kind of S-curve, an S-curve where at the bottom of the S, where you start drawing near the bottom of the page, that's sort of the low occupation fraction, where essentially you've only got one or two civilizations out there. And then you can have, on the other end of the S, a regime where basically every single star has been occupied. And you might imagine this with sort of a von Neumann probes or some kind of aggressive civilization that expands across the entire star systems and builds a galactic empire. So you can imagine these two extremes. And if you're a SETI optimist, you know that upper extreme is ruled out, right? At least we think it is. We don't think there's that galactic empire out there. And so if you're a SETI optimist, you are banking that you live on the S, on the neck of that S curve. That's where you must live. Another way of saying that is that, if you extend the S out now, imagine drawing a very wide S so that, you do the flat part for a very, 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 very long time, and then you draw a sharp S, and then you draw a very, very long flat part at the top of the S. The reason why you can do that is because, of course, we have no bounds on how far this S can go. It may very well be that really this X-axis on this plot would be essentially the probability of life beginning on a planet. And we argue that there's no real bounds on that constraint. It could be that it's an extremely small probability, a very large probability. And so this essentially extends out to infinity. And to live on the neck of that S-curve is an infinitesimal volume, essentially, in this parameter space. It's just incredibly unlikely that if you were to choose any random probability, it would happen to be a probability that lands right in the neck of that S-curve. So that's a completely analogous way of thinking about the problem. So we rederive the Drake equation where we create what we call a birth-death balance. So now you cannot have more civilizations than there are stars in the universe. It's kind of bounded by the ecological bounds of the system, of the galaxy in this case. And furthermore, it has what we call a steady state assumption built into it, which is really the only assumption in our work, that the population of the galaxy is not rapidly exploding nor rapidly declining. So it's reached essentially a steady state. So maybe that steady state is, say, one civilization every billion years or something appears. Like that's the steady state at which we expect civilizations to appear. But it could be anything. We don't know what that number is beforehand. That's all we assume, that the number of births equals the number of deaths over long periods of time. And with that simple assumption, you can basically take the Drake equation and prove that it actually equals what we derive in this paper, which is this Jaynes-like Bayesian formalism of these two extremes. So it's kind of nice that we can mathematically prove that these two, the classic approach that Drake wrote down, with a bit of a modification to account for the ecological threshold of how many spaces there are for civilizations to live, if you include that modification, it now naturally equals the way that these classic Bayesian statisticians would have thought about the problem in terms of being either abundant or very, very rare. So I feel like we've kind of closed a nice loop here, and that's kind of what worries me. It's almost like it's a little bit too successful. I want there to be life out there, so it kind of a little bit depressed me when I wrote this paper, to be honest.
I have long ago killed such ambitions of wanting it to be out there. I just want to know what is.
Yeah.
And the bottom line is that we're far enough in the game. It's actually interesting to contrast this, because look at the very beginnings of SETI, which really started in the, even before the 19th century, that Mars. Let's build giant geometric patterns in the Sahara, or let's light giant bonfires so the Martians can see us, which turned out obviously to be a very naive way of doing it, but you had to start somewhere. And now we're getting a finer and finer point. We're sharpening the pencil down to things that really, with your paper specifically here, really look like what we observe. In other words, this gives a framework to start thinking about scarce life. But within this, there's something that does scare me.
Mm-hmm.
The longevity of life. When the petri dish runs out of food, as you were talking about, then that civilization goes away. And if it has to travel tens of light years to find another suitable place that may be too tall of an order, meaning that not only do you have rare life, you have rare intelligence that only lasts a very short time, which would definitely explain what we see, right?
Yeah, I think the issue of spreading, of course, is an idea which has been investigated extensively by many previous groups. I have to say, when I was writing this paper, I kind of almost feel inspired to write my own version of this model to investigate it. But people have done this. They've simulated a galaxy. Of course, you can't really simulate 100 billion stars. That's just too many for our computers to simulate. But you can simulate a galaxy with like 1 million stars or something. And you can let them even move around now in the latest simulations. They're not just static. The ones in the 1970s and 80s, the first models, they just assumed a totally static galaxy where nothing changed. Now we have these more sophisticated models where stars can actually move around, especially simulations by Jonathan Carroll Nellenbach and Adam Frank's group. They've been doing this kind of work. And then you can spawn a civilization and let it spread out at pretty modest speeds. I think they were doing like Voyager type speeds, like 30 kilometers per second. And they assumed they just had like a 3D printer and some kind of self-replication process. It's kind of scary because the range isn't usually such a big deal. Given that these journeys are, hundreds of thousands of years, that seems terrifying, but there's no real reason why a piece of technology shouldn't be able to last that long. And when it arrives on a different system, it can just continuously spread. And over, I think, a span of about 10 million years or so, you can, maybe even 100 million years, you might be able to totally colonize the Milky Way. So I think on this timescale, there's enough time to colonize the Milky Way about 40 to 50 times over in its lifetime, even without having warp drives, even without having anything faster than Voyager. Basically, you can do this. So that's kind of a hard argument. And I know there's lots of people, when I make videos about this, and I talk about this, people get annoyed. They're like, why do scientists always assume civilizations will spread out like this and do this behavior? But I think it's really hard to argue it won't happen. It is, to me, this is the hardest version of the Fermi paradox, or really it's really Hart's paradox. He called it, Hart was the original person who came up with this idea, and it's called Hart's fact A. And it's the fact that, we don't seem to live in a galaxy that's been totally taken over with these 3D printers, as far as we can tell. And it's really hard to argue against it because we're already trying to do it. And we've done it throughout human history. We have tried to spread to different countries, to different continents, to different environments throughout human history as a way of increasing our population and thus, mitigating the possibility of extinction. It's just a natural human instinct to want to do that. I think probably every species has such an instinct. Furthermore, we are engaged in it right now. If you listen to Elon Musk talk about Mars, that's precisely his motive. He wants to, as he says, keep the candle of consciousness or the flame of consciousness alive. And his primary motive is to make human a multiplanetary species to essentially provide some protection against the extinction of human life. Maybe something goes terribly wrong on the Earth, and so we have a backup plan. So any species that cares about survival must have this instinct that putting all my eggs in one basket is inherently dangerous. I should want to spread to somewhere else. And not just being in one planetary system, but of course spreading to other stars, because who knows, a supernova might go off nearby, and it doesn't really matter then that you have a Mars colony, because both Mars and Earth are going to be fried. So of course you want to have multi-stars, and then even eventually multi-galaxies. Why not? So there's no obvious reason why any species with the most basic desire that we can imagine of wanting to survive, and if it lacks the ability that it wants to survive, then how on earth did it even evolve? Like what's going on there? So for anything that has that basic criteria of wanting to survive must surely have this desire to want to spread between the stars. And we know it's not beyond, the scope of imagination that technologies could do that. So this for me is actually a very strong problem, and it really does bother me a lot. And I suppose when you connect it to the result of our paper, that we didn't try to talk about these simulations at all in our paper of von Neumann machines spreading across the galaxy like this, but if you connect it to our paper, they come to the same conclusion, right? And that's that this behavior, this type of life, this type of technology just doesn't happen. And if that doesn't happen, that's a pretty strong data point.
It would be tempting to say that this is all pessimistic, but I'm going to add a positive note as somebody that wants to be a SETI optimist, really badly wants to be one. But if you have a expanding humanity, doing what life does, which was what John von Neumann's original idea was that life does this. Life is a sort of von Neumann probe. It self-replicates, it expands if it can, and so on. And he just simply extrapolated that to machines. Well, if we go out and Elon is successful and we go to Mars and then we go to other star systems very slowly and we expand slowly outward, what you end up with eventually is Star Trek world, exactly as Star Trek put it out. It said that, well, the reason all these you're all bipeds and everything is because you were seeded by us, an ancient civilization. That's eventually the future for humanity if we go down this route, because after 1 million or 2 million years of separation, especially with technology and genetic engineering and everything else, you are going to end up, even though your origin is the same, starting out as human, you're going to be very different from that civilization that was founded 1 million years ago by Earth versus your civilization that was founded 1 million years ago by Earth, effectively meaning that you eventually end up with alien civilizations anyway. They're just cousins, not completely separate instances. What do you think about that scenario?
Yeah, it kind of reminds me of like Dune or something a little bit, right? Where you have this or even the Foundation a tiny bit. But yeah, the idea of culture certainly diversifying has been explored in science fiction a lot, and even to some extent, as you probably know better than me as a science fiction writer, the idea of complete evolutionary paths diverging. I've thought about this a little bit in the context mostly of the Earth, actually, rather than other star systems, and mostly from the idea of people want to make contact with aliens, right? I think there's like an itch. We want to one day talk to an alien and let them know that we were here and these are the things we've achieved. And I have kind of a radical claim that the most likely alien we're ever going to make contact with is our future descendants, essentially. So kind of building upon what you were just saying, John. So my argument is that there's 1 billion years left of habitability, of complex life habitability on this planet. And that's a very long time. I mean, just think the dinosaurs were extinguished 65 million years ago. So that's like a blink of an eye on a 1 billion year time scale. 1 billion years is a very long time. In fact, if you go back 600 million years, that's the first multicellular life. So 600 million years ago, everything was single-celled. So you've got more than that again still to go on the clock. So there's a lot of time for evolution still to play out. And it's starting, of course, from a very high position because we already have hominids, we already have octopuses, we already have ravens and dolphins and humpback whales, things which have presented many indications of intelligence. And so whatever happens to humanity, Maybe we'll have, some slow decline or something, or crash out. But in either case, I'm pretty optimistic that some genetic relic of intelligence somewhere in the animal kingdom will be persistent, and it will keep cropping up, because the fact it's already appeared in multiple aspects of the animal kingdom implies that it has evolutionary advantages. It clearly does to humanity. That's our main. We're not particularly fast, we're not particularly strong. The only thing we've really got going for us is that we're smarter than everything else, and that's how we basically took over the world. And so it seems obvious that as long as this evolutionary advantage exists, maybe it's a very rare advantage to get going, but it's now here. It's hard to get rid of it. It's like a virus, a mind virus, if you like, but in a different sense, an intelligence virus that's now on this planet. And I think it's going to be very difficult to eradicate intelligence in the same way it's very difficult to eradicate life totally from any environment. And so my claim is that intelligence will now just keep re-emerging on this planet for the next billion years, in all different sorts of forms, and many of them, or some of them, will have the ability to develop technology down the road as well. And so we may be the first. It seems very likely to me we are first. I know there is this Cyrillian hypothesis, which says, well, slow down there, be a little bit careful, but there's certainly no relics on the moon, as far as we can tell. We appear to be the first human, we appear to be the first Earth goers to reach the moon. There doesn't appear to be any other footprints or anything like that on the surface of the moon. And so that makes me think we are the first, but maybe not the last. And there will be many opportunities for future civilizations to reemerge on this planet who will essentially be alien to us. And we can communicate with them, not in a two-way sense, but in a one-way sense, by leaving monuments behind, by leaving time capsules behind for them to discover. And so to me, that is the most likely. If I had to just choose one method to try and communicate with aliens and put all of your eggs into one basket, that to me is the most likely path to success.
That actually brings up something somewhat unrelated, but it actually is. And they have made, leaps and strides, especially with artificial intelligence, and trying to figure out whales and what they're communicating in between each other.
Yeah.
And trying to begin to figure that out. And that, to me, offers us the closest thing we're going to get, probably, to talking to an alien. But in a way, it's just as good, because we are not whales, and they are not us.
Yeah.
And it would be, this is something that's within our grasp to figure out, is animal communication. And then that sort of in many ways tells us the same thing that talking to an alien would. They're just not going to give us a complete model of physics or anything as a gift. They're just going to show us what is close to an alien mind as we can get looks like. What do you think? How does that play into it? Does that actually satisfy you? If we can start to decipher whale communication, beluga whales being able to talk to each other, does that get close to being able to talk to an alien in your mind? In my mind, it does.
Yeah, I think so. Obviously, there's lots of similar heritage that we share with a whale. We're both mammals, so we're going to be much more genetically similar than any alien that we encounter. But I agree that if we can't successfully communicate with something as closely related to us as a whale, it seems pretty unlikely we'd succeed with other forms of intelligent life out there, which are possibly far, far more alien than we can even imagine. So it's really important work, and I was really pleased to see that research reported quite widely recently. It also opens the door to connect back to my paper of this other scenario, which we kind of dismissed in the paper, and I dismissed it in this conversation, but maybe there's some crack of opening that up. And that's the F equals 1 scenario, as we call it, which is essentially 100% of stars have intelligent life around them, or a very large fraction of them have intelligent life around them. That seems implausible, but it is possible that they are, more different to us than we can imagine. But they are still what we would consider intelligent life forms of some kind. So, for instance, a whale might fall into that classification. And another example I often like to play with as a fun idea is the idea of just a sponge, right? A fungus or something that's like taken over an entire planet, and it is in its world the only version of life it's ever seen, because it's just a unilife planet where there's just one type of cell, and it is just that cell over and over again all over the entire planet. And that thing could be extremely intelligent, right? Because we know that networks of cells together, and networks of animals, even like bees and ants, can form a form of intelligence that's higher than the individuals. And so we could imagine very different forms of intelligence out there, but that would now sort of scratch this itch a little bit of, well, how can we have this F=1 scenario? It's just that they are out there, but they're so different to us that there's no bipedal, humanoids who think the way we think, who use mathematics, who build technology in the same way we sort of think about technology. And so they're just so different to us that it's not that they're not out there, it's just that there's no real prospect of a meaningful conversation or a prospect of communicating with them in the near term. So that's one possible way out of it. I tend to be a little bit skeptical about that because it's making a lot of assumptions about the diversity of how broad it has to be to get out of this problem. I guess the problem with the kind of what you might call the grabby aliens hypothesis, or these kind of von Neumann machines, is that even if just 1 out of a million do this behavior, then you're basically screwed, right? You don't require very many of these things for it to become a very big problem for the galaxy. So you kind of now have to have a universe where we are the only species that behave the way we behave. Like, no one else out there ever has the intent or desire to build machines and spread themselves, which, as I said earlier, I think it's hard to imagine. I find that hard to justify. That behavior wouldn't repeat elsewhere, but it is a possibility. I think the other way out of it is that maybe we happen to live in a galaxy that is very lonely, but most other galaxies are full. So that's again kind of consistent with the F=1 scenario, that maybe 99.99% of galaxies have had an intelligent species emerge in them in the past. That intelligent species colonized the entire galaxy, and now there's nowhere to live in those galaxies because it's just all computers, basically. And then naturally it would make sense that we would have to be born in one of the very few galaxies left where that had not happened, because we could not have been born elsewhere. It would be impossible for us to have been naturally emerged in a galaxy where every single planet is just computers. We have to would emerge in a one of the final surviving natural galaxies, natural worlds in the universe. So that's also quite possible, and it raises the case for doing extragalactic SETI. I think that's a really interesting experiment to try in the future. There have been some experiments so far, but it's really, we just scratched the surface of that. But do other galaxies show indications of total colonization? Because that would very naturally scratch this itch. I think if we determined that, or determined an absence of that, it would provide another very important data point, and especially that connects to the grabby aliens hypothesis, which really puts forward the idea that there's aliens everywhere and we just have to live in one of these pockets where this hasn't happened.
Yeah, that's something that I've always wondered about, is that I think there's a certain daunting aspect to doing extragalactic SETI, because it's just the distances are so far away and the resolutions are just so terrible. But at the same time, we have a very nice local group, and Andromeda is just sitting there.
And getting closer. Yeah.
And getting closer. Yeah, where eventually it's going to be, if it has a machine civilization that is completely controlling it, someday it will control the Milky Way when they collide. Mm-hmm. So I tend to think that is an area that people have looked for red spirals and Dyson spheres and infrared and all that stuff, but that's about it. There hasn't really been very much extragalactic SETI, and I would like to see more of that, because it just seems like leave no stone unturned in this question.
Yeah, and I think it's not just that. I think it's actually it's a totally decoupled experiment. When we look at Mars for life, for instance, a complaint that I might have is that it's not decoupled from us. And that's why I think you brought up earlier the idea of Europa and Enceladus as being better, because they are what I would call decoupled. So there is the possibility of life transferring between Mars and Earth. And so if we discover life on Mars, we don't really know if it's genuinely a true second abiogenesis event, or whether it's just a cousin of us that got knocked off the Earth, or vice versa, and there's some transfer. For Europa, maybe it seems harder for that to happen because it's under so much ice and it's just further outside the gravitational well of the sun. So it's hard to imagine that transfer happening. So that's why I think Europa would be a much more interesting abiogenesis experiment than Mars would be. And the same way, other galaxies are maybe not totally decoupled from us, but they are certainly more decoupled from us than nearby stars. If there is a roaming, this behavior of roaming civilizations creating empires, then we have this kind of coupling problem happening. Whereas with other galaxies, they're hopefully, if we look far enough away, so far away that there's basically no chance of that that interaction happening, and thus they truly represent fair experiments, uncontaminated by any selection bias. Whereas when we look at our own galaxy, it is now sculpted by selection bias because we are only here because we're here. It's that weak anthropic principle that raises its head so often in discussions of alien life and our existence. We may live in an empty galaxy, but we can't conclude, therefore, that means all galaxies are empty. It may be that we live in a galaxy that's empty because that's a necessity to our existence. And that's where, looking at other galaxies is so powerful because it breaks that dependency and it gives us a truly fair and objective experiment.
I love the idea of us living in the backwater of a backwater galaxy.
Yeah.
In other words, we're in an unimportant position in an unimportant galaxy, and that is what creates us.
It may be, but in the other way, we may even be, in this F=1 scenario, we may be on the other side of the coin quite rare, and thus some would argue maybe special in that sense. If maybe most of the galaxies have already been colonized and we live in this one lonely galaxy, that would make us kind of unusual and at least unusual amongst galaxies, but not unusual amongst observers. We'd be actually totally typical for all of the species which naturally emerge, intelligent species which naturally evolve and develop. All of them would necessarily have to live in lonely galaxies. And so in that sense, we would be totally typical, but amongst all the galaxies themselves, we would be very unusual. Normally, when you're talking about these principles of like mediocrity and Copernican, it's about the observers, the representative observers that really matters, not the abstract space of number of galaxies or number of stars. So it would be totally consistent, actually, with mediocrity principle. But I'm always a little bit averse to discussions of specialness, because as soon as you start talking about specialness, that Carl Sagan voice starts coming into your head. That there's this kind of compulsion to assume that we're totally humble and we're not very, Avi Loeb often uses this language, we must not assume we're the smartest cookie on the block, this kind of stuff. And I'm a little bit averse to that language just because it's emotive. And I just don't think emotional language serves us very well in discussions of intelligent life in the universe, or life, or any scientific question, to be honest. As soon as we start saying, we must be humble, or you are arrogant if you think this, then you're making an emotional appeal, and then it's very dangerous for me. I think then you're almost manipulating people a little bit by the choice of words that you're using. So I'm a little bit hesitant to use that kind of language of specialness, and I just prefer to say, the statistical probabilities involved. But it is something I just want to raise, because sometimes I think viewers will hear that and they'll probably think, oh my God, this guy must be so arrogant to think we're alone in the universe. But that's precisely an emotive argument that you're making. And it's not a scientific argument to make that argument. You can make a scientific argument, but do so without invoking that kind of emotional language. In my view, that doesn't have a good place in science.
That underpins my thinking. What is, and I simply want to know what is.
Yeah.
And that's as far as it goes. And I think that's the useful way to look at it, because you don't have those emotive, tendencies and things like that. And, it's all too easy to have, I want this to be true to come in, which we see that everywhere.
Right.
But there is, and I'll end on this because you have a hard out, and I will end on this. If intelligence is rare, then we are absolutely safe from alien invasion. We will never get invaded like Independence Day, and I take comfort in that too.
Well, the biggest threat to humanity is humanity. I think we all know that. The biggest threat to humanity is not the Independence Day scenario. We actually watched that on July 4th with my kids the other day because I just love that film. It's such a classic film. But, it's Hollywood. It's Hollywood. I don't think anyone seriously thinks that's the most likely outcome of our destruction. The number of challenges we face as a species right now have never been higher, and we are really at this point where people are wondering about this great filter, which could obviously explain the Fermi paradox, that there's some event that happens. It's either in our past, the evolution of intelligent life might be a very rare phenomenon, or it's something that's about to happen. It's just round the corner, that we are on the verge of total collapse. And that doesn't even have to be anything dramatic. It could just be a slow decline. Economic output and technological development, scientific research just slowly declines over the next few centuries, and we just recede further and further back. And that's also a way that we would resolve the Fermi paradox, right? It's a slow, great filter. And that's almost, to me, like the worst version of it, because I think when we get older in life, it's kind of the thing that we fear is the loss of our faculties and the slow decline of our bodies. And it's not like a glorious, instantaneous death, but a slow pulling away of all the things we used to be able to do. And for me, that's kind of the greatest fear I have about our civilization, is that we will just, like the frogs being boiled in the water, just not notice the slow backwards motion of our capabilities. So to me, that looks right now as one of the things I'm most concerned about. And I think the idea of Independence Day is fun to play with, but it's not my highest concern for what's going to be around the corner.
Well, I think the very worst situation that we could end up in is and this nicely rounds out the conversation, that we decline and just sort of begin to flatten out during the rise of the octopus, and the highly intelligent technological octopus takes over, and we are forever its housekeepers.
Or AI even, who knows? Yeah.
Or an AI octopus. One can go in many directions on this. All right, David, it's always a pleasure to talk to you, and I look forward to the next paper. Everybody can find David's paper linked in the description below, and to his Cool Worlds channel, where he gave a full presentation, a very, very concise one, on this very subject. And everybody should check all of that out. David, I can't wait for the next paper. What's in the works for you?
At the moment, we're really gearing up for our X-Human observations in October with JWST, so we're pretty excited about that. And then on the SETI front, I'm thinking a lot about how to sort of resolve ambiguities in detections. If you detect something that looks like it could be alien, how do you truly know that it is alien? So I'm thinking a lot about the false positives and how do we remove those in a very general sense. So yeah, stay tuned. I'll have some more about that in the future.
Stay tuned indeed. All right, thank you, David.
Thank you.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.